Hey everyone, I'm Cameron. I put together this presentation for my spring 2021 CS504 class about advanced forensics and malware analysis. I'll be talking about anti-disassembly techniques that are commonly used in malware. The material I'm presenting is based on chapter 15 of the Practical Malware Analysis textbook by Michael Sikorsky. Let's jump into it. Here's a quick outline of what I'll be talking about. First, I'm going to discuss the background of anti-disassembly techniques. This includes a bit about how disassemblers usually work and how they can be undermined. Next, I'll give a brief overview of the techniques covered in the text, followed by a closer look at each of them, and I'll describe how to get around them. I'll give a quick summary of all the fixes for the anti-disassembly techniques I discuss. The last big part of this presentation is a walkthrough of the labs provided in the textbook. These will take up most of the presentation. Finally, I'll conclude with a summary of what I talked about and tell you where you can learn more about anti-disassembly techniques. We talked about disassembly in class and in previous chapters in the book, so I won't go into too much detail about it. In brief, disassemblers work by analyzing the bytes that make up an executable file and interpreting them into instructions. There are two major techniques by which this is done: linear disassembly and flow-oriented disassembly. Linear disassembly is the simplest. It ignores instructions like jump and call that dictate control flow, simply going from one collection of bytes to the next and producing readable assembly instructions. A linear disassembler is assuming that all the bytes it encounters are just a continuous block of instructions, but this is rarely the case. Most binaries instead would make liberal use of control flow altering instructions and contain a mixture of data and instructions rather than a continuous block of instructions. Flow-oriented disassemblers like IDA-Pro are better at addressing this. When a control flow instruction like a conditional jump is encountered, it'll add the two possible branch locations to a list of places in the binary that need to be disassembled in the future, and then it works its way through each of these branches until disassembly is complete. In this process, the flow-oriented disassembler also makes some assumptions. For example, most disassemblers like this will process the false branch of a conditional jump first, and this can be problematic if both branches interact with overlapping sets of bytes, maybe even at different offsets. This might be a bit confusing now, but hopefully it'll make more sense when I get into some examples later on. The techniques Sikorsky covers in the book are false conditional branches, including jumps with the same target and jumps with a constant branch, or constant condition, impossible disassemblies, function pointers, return pointer abuse, misusing structured exception handlers, and thwarting stack frame analysis. On the next few slides, I'll give an explanation for each of these. First up is jump instructions with the same target. In the book, the author states that this is the most common anti-disassembly technique. A good example of this is when a jump 0 instruction is immediately followed by a jump not 0 instruction pointing to the same location. When the disassembler reaches the jump 0 and jump not 0, it adds the jump address to its list of places to disassemble later and moves on. When it reaches the following line, it disassembles it into a call instruction. However, both jumps actually target a byte that is inside that call instruction. Since the disassembler trusts what it disassembled first, the bad call instruction is kept in the disassembly. To fix the disassembly for continuing analysis, only the bytes that are jumped to should be interpreted as part of the instruction. In this case, a byte of data is left out since it throws off the assembly. And that's called a rogue byte. And in this case, it's the E8 in the example image. Next up are jump instructions with a constant condition. And this is another technique that's really common. Their author also refers to it as a false conditional branch, since a conditional instruction is used, but only one branch will ever actually be taken because of the context it's used in. Like before, when the jump is reached, the disassembler adds the target location to the list of places in the program to disassemble it in the future, and then continues on. It interprets the next byte as being the beginning of another instruction, in this case the jump instruction. When the disassembler works on the target of the jump 0 instruction later on, it comes across the bytes it already disassembled and trusts its original disassembly. Once again, the fix is to cut out the rogue byte, which in this case is the E9, making the disassembler interpret the following bytes as the correct instructions. In the previous examples, the rogue byte could safely be converted to data and ignored while preserving the functionality of the program. But this won't always be the case with rogue bytes. They can be included in such a way that they are part of two valid instructions that the machine will actually run at runtime. Even though the disassembler must make assumptions about how to correctly interpret and display bytes, the machine at runtime doesn't have this limitation. Consider the snippet in figure 15-4. When the machine is running this, it first interprets the jump instruction the jump -1 instruction, stepping back 1 byte, then reading inc, EAX, and finally decrease EAX. This is a valid series of instructions, though ultimately useless. These can be placed anywhere throughout a binary to confuse the disassembler, since it can't have a display for more than one interpretation at a time. And that disrupts the chain of validly disassembled bytes. This can get rather complicated, as can be seen in figure 15-5's multi-level inward jumping sequence. To fix issues like these and continue analysis, you need to carefully consider the effect these have when actually running, then either convert bytes to data or convert them to no-ops so that the flow of disassembly and the functionality of the program are preserved. The next few anti-disassembly techniques I'll discuss work by obscuring the control flow of the binary that's being analyzed. So here we are with function pointers. A disassembler doesn't keep track of the runtime context, so it struggles to properly cross-reference function calls with addresses that are computed during runtime. In the example at the right, IDA notices that at label number 1 that EBP plus var4 is equivalent to the address hex 4011C0, but it doesn't keep track of the context well enough to create the same cross-references for the function pointer used at labels 2 and 3. This makes analysis difficult since it can be hard to tell what function is being called in large programs. Standard usage of function pointers is already hard enough for disassemblers to properly label and keep track of, so when malware authors use non-standard methods for constructing function pointers, the disassembler has even more problems. One way to address this is to manually add cross-references that IDA missed, making it easier to analyze. You can do this by using the add code xref function that's provided in the IDA scripting language. Another technique that makes analysis difficult by obscuring control flow is return pointer abuse. The retn instruction normally only appears at the end of functions, but there's nothing that really enforces that. Return behaves as a combination of the pop and jump instructions, and malware authors can take advantage of this to confuse disassemblers. Consider the example on the right. The call instruction pushes hex 4011C5 onto the stack, leading execution to the following add instruction. And then at that add instruction, since var4 is a pointer of value -4, ESP +4 plus var4 just ends up giving you ESP. It's +4 -4. And at this point, it points to hex 4011C5. And then in the add instruction, adding 5 to this gives hex 4011CA. So when the return instruction is called, the rest of the actual function is jumped to, and the execution continues. In this way, the disassembler doesn't make a cross-reference that reflects the logical outcome of the assembly instructions, and it thinks the function has ended since the return instruction was encountered. To fix this, the useless, misleading instructions can be patched into no-ops, and the function boundaries can be redefined using Alt-P in IDA Pro to reflect the function's actual behavior. In the example, you convert the call, add, and return instructions grouped together at the top into nops. Another technique used to obscure control flow is the misuse of structured exception handling. When an error is encountered in a thread, execution can be handed off to special functions to recover from the error. These functions are called structured exception handlers since they are chained together to handle the various error conditions that might occur in a program. Similar to the function pointer problems discussed earlier, the author of the binary could craft pointers to the exception handling functions in a way that the disassembler has a hard time recognizing. After that, they intentionally cause an error condition to jump to that exception handler. Since the author can craft the exception handling function, it can contain whatever functionality they want. In the example shown, the pointer to the exception handler at address hex 401080, labeled 1, is assembled by the move and add instructions at label 2. The exception is then triggered by the divide 0 at label 3, forcing the program to enter the instruction handler. Or excuse me, the exception handler. Since it's never directly called, the disassembler misinterprets the exception handler bytes at hex 401080 as data. To continue analysis of a binary that does this, you need to identify locations where errors will be triggered, find where the exception handling functions are located, and switch them from data to code to reveal their functionality, and then you can continue your analysis. This is just a quick summary of how this works, and structured exception handlers can be a bit confusing, so I highly suggest taking a look at the section in the book about it and maybe reading up a bit more about structured exception handling. The final anti-disassembly technique I'll discuss is thwarting stack frame analysis. Many disassemblers, including IDA Pro, have some sort of stack frame analysis functionality that attempts to identify what variables are involved in a function. However, stack frame analysis is not straightforward and some assumptions have to be made. Malware authors can exploit these assumptions to mislead the disassembler into creating nonsensical stack frames with incorrect variables. In the example on the right, in addition, an extra column of information is shown that represents the stack pointer, and you can enable this in IDA's general options menu. At label 1, the stack pointer is negative. This shouldn't happen with a normal function since it can damage the calling function stack frame, and this is a telltale sign that the disassembler has made a mistake. In the preceding instructions, we can find where the problem occurred. At hex 401549, the stack pointer is compared to hex 1000. Because of how the OS manages memory, the stack pointer will always be larger than hex 1000. But the disassembler is fooled by this and interprets the bytes at hex 401556 as valid instructions, even though they will never be jumped to when the program is actually executed. Because of this, IDA's built-in stack analysis functionality completely misinterprets this function. You can use Control-K in IDA to examine a stack frame, and you can press Y to make IDA attempt to give a function prototype of a stack frame that it's analyzed. And if you try to do that with this example function, it gives you a ridiculous function prototype that takes 62 arguments. Here, I'll summarize some of the things you can do in IDA Pro to fix a disassembly when binary uses anti-disassembly techniques. First and foremost, you can use the C and D keys to convert bytes between code and data, respectively. Second, when you encounter rogue bytes or impossible disassemblies, you can convert bytes to NOP instructions while preserving functionality to make analysis easier. Next, when you encounter techniques that mess with control flow and make IDA misinterpret the boundaries of a function, you can redefine those function boundaries using Alt-P. And when you encounter function pointer usage that makes the disassembly difficult to analyze, you can use the add code cross-ref function in IDA script to make the analysis easier. This concludes my overview of the main part of Chapter 15. Next, I'll be talking about the labs from the chapter. I'll discuss the steps taken in each lab as well as the answers to each question. These are also detailed in the book, but I've taken screen clippings to show my reproduction of the analysis steps. And a bit of what I encountered differed from what was shown in the book walkthroughs, but I was still able to uncover enough about the executables to reach the same conclusions presented in the book answers. And without further ado, let's jump into it. Here are the questions for Lab 15-1. Just kind of keep these in mind as we go along. Question 1 is, what anti-disassembly technique is used in this binary? And then we have, what rogue opcode is the disassembly tricked into disassembling? 3 is, how many times is this technique used? And 4 is, what command line argument will cause the program to print good job? Analysis is a lot easier if you can see the bytes in each instruction. And to enable this in IDA, you click Options, then General, which opens up a window. In the Display Disassembly Lines part, put a number in the box for the number of opcode bytes to display. I went with 5 since this is the most I need for analyzing these labs. And then if an instruction has more than this, IDA will just display a plus after the 5th byte. The first thing you'll probably notice when you go to analyze the main function of this executable is that there are red highlights in a few places. This means IDA thinks there's something suspicious there, and in this case, the address being called is invalid in the current disassembly since it indexes into another instruction. Since the instruction XOR EAX EAX sets the 0 flag, the jump 0 instruction following it will always be taken. But as mentioned earlier, IDA will usually assume that jumps aren't taken and disassemble the following bytes under that assumption. So it thinks there's a call instruction there. The fix for this is to cut out the unused byte and resolve the following bytes into valid instructions. After converting the target of the jump instruction to code, the real instruction that is jumped to is revealed. And to do this, you want to convert the fake call into data by pressing the D key. And then from the byte that is actually jumped to, use the C key to convert the data to code. And this leaves the rogue byte by itself, revealing the actual instructions. Note that the rest of the data needs to be converted to code as well, with the newly found offset between instructions. And with that, we've got our first two answers to the questions in Lab 15-1. The first answer is the anti-disassembly technique used in this binary is a false conditional branch in the form of the instructions XOR EAX EAX followed by the jump 0 instruction. And then the answer to question 2 is IDA is tricked into disassembling the rogue opcode E8 following the jump 0 instruction, which results in the fake call instruction. The third question was about how many occurrences of the false conditional branch there are in the program. IDA's red highlighting means it thinks there's something suspicious at that highlighted location, as I mentioned before. And sure enough, there are 4 instances of the false conditional branch around each of these locations, leading into a fake call. However, there's a 5th hidden occurrence that is revealed when fixing the second occurrence. In the Lab 15-1 binary, when you fix the false conditional branch occurring at the address hex 40101F, a 5th one is revealed at the address 401033. So it's important to note that these false conditional branches can be nested. And using these techniques, we find a total of 5 occurrences of the false conditional branch technique in the lab 15-01.exe file. The final question was about what command line argument will make this executable print the message "good job." Now that we've fixed all the false conditionals using the technique described previously, we can make IDA recognize where the main function actually ends. To do this, you select from the top of the main function at address 401000 all the way down to the return instruction at 401077 and press the P key. And this will rename variables to match the function call and make tracing through the disassembly much easier. With these fixes applied, IDA's stack frame analysis is able to determine the variables for the main function are argc and argv, and then it properly labels them all the way through the program whenever they're used. In the screenshot on the right, I've highlighted the compare instructions that make it a lot clearer what the functionality of the program is. The first comparison checks the argc variable to make sure there are 2 arguments supplied when the program is called on the command line. The first argument is just the name of the program itself that you use to invoke it, so the following comparisons examine the contents of the second argument, influencing how the program behaves. The second comparison checks that the first byte of the second argument is hex 70, which if you decode that on an ASCII character table is lowercase p. The third and fourth comparisons check the next characters out of order, so you've got to be a little bit careful. The third comparison checks for an ASCII lowercase q, and the fourth checks for an ASCII lowercase d. So the command line argument that is expected for the executable to print the good job message is lowercase pdq. And in the GIF, you can see that when the program's executed without a second argument, it prints the "son, I am disappoint" message. But then when I enter the pdq as the argument, it prints "good job." And that's it for Lab 15-1. So moving right along, here are the questions for Lab 15-2. Again, keep these in mind as we go along. First question is, what URL is initially requested by the program? Number 2 is, how is the user agent generated? Number 3, what does the program look for in the page it initially requests? And number 4, what does the program do with the information it extracts from the page? When we open up the lab15-2.exe file in IDA and start reading the main function top to bottom, we find a false conditional branch at hex 40115A. The test ESP instruction will always result in a 0 and is immediately followed by a jump not 0 instruction. So this is an example of a jump instruction with a constant condition. As before, this can be fixed by selecting the fake call that is indexed into and converting it to data, then excluding the rogue byte and converting the rest of the bytes back into valid instructions. You'll find another jump with a constant condition at hex 4011D0, this time with an XOR EAX instruction followed by a jump 0 instruction. And the same fix can be applied to that one as before. The next anti-disassembly countermeasure we find is at hex 401215. The jump instruction points to an address inside itself, and that's an example of an impossible disassembly countermeasure. And to fix this, we convert the jump instruction to data, then patch the first byte into a no-op. And this way, the logical flow of the program is preserved, and analysis in IDA can continue. Next up, we find some jump instructions with the same target used at hex 401269. Once again, we can fix this by converting the call instruction to data, then leaving the rogue byte out. Convert the remaining bytes back to code to reveal the actual instructions. The next anti-disassembly countermeasure we find is a kind of hybrid. It's both a false conditional branch and an impossible disassembly at the same time. To fix this, you convert the jump instruction to data, then resolve the bytes following it back into instructions. And from there, you can follow the program flow into the fake call instruction. And after that, it's the usual fix of cutting out the rogue byte by converting to data, skipping the rogue byte, and then changing everything else back into instructions. Once all the previous fixes are applied, you'll have a continuous set of instructions that accurately represents the main function. The book recommends patching all the rogue bytes into NOPs, but I found this unnecessary after trying it both ways. And you can now select the whole main function from hex 401000 down to the return instruction at 40130E. And then you press P to make IDA recognize it as one function. This names the variables throughout the function, making it easier to analyze, and allows you to use IDA's graph view on this function. The variable names it chose during my analysis were a bit different than the ones that were shown in the book walkthrough, but I was still able to just continue the analysis just fine. Switching over to the graph view, we can find that the internet open URL A function is called and apparently uses a string produced by the function at hex 40386. And when we take a closer look at that function, we can see that it manually constructs a string by moving around some hex values. The string is then copied to the heap via the stirdupe function, and a pointer to it is returned. And with all that, we can finally answer question 1 by decoding the hex values back into ASCII characters. And here it is. The URL initially requested by the program is practicalmalwareanalysis.com/bamboo.html. By building the string manually like this, the URL doesn't appear in the binary as a regular string, but only shows up in memory at runtime. This technique is used again in the function at hex 40130F to build the string accountsummary.xls.exe. To make analysis a little bit easier, you can rename the functions using the N key in IDA. The book recommends renaming them build URL and build file names, so that's what I went ahead and did. The next question in Lab 15-2 asks about how the user agent string is generated. The user agent field is set by an accompanying function called internet open A. And during my analysis, IDA named the user agent variable SZAgent, but in the book walkthrough it was called name. The SZAgent variable is populated by a call to the get hostname function. And we're getting pretty close, but this isn't quite the whole answer. So we'll get to that in the next slide. The instructions between hex 401073 and hex 40113F shift each character in the SC agent string forward by 1, and it loops around at the end of each character type such that Z's shift forward into A's and 9's shift forward into 0's. So the answer to the second question is that the user string is generated by getting the hostname, then shifting each character forward by 1. And just as a reminder, the next question was, what does the program look for in the page it initially requests? The HTML page downloaded from the Internet Open URL A function call is stored in a variable that was named buffer during my analysis. And after this, the function stir is called twice, interacting with the buffer. Or the buffer variable, I should say. The stir function is used to search a string for a substring. And IDA has labeled the substrings being searched for and commented them, so it's apparent that the program searches for a string with the beginning delimiter bamboo : and an end delimiter of : And this gives us the answer to question 3. The program looks inside the HTML page it requested to find a string that is delimited by bamboo : and : This string is then placed into a variable that was named lpsz URL during my analysis. And after this, the lpsz URL is used to download and execute another file called accountsummary.xls.exe, which is the answer to question 4. And moving right along, we're on lab 15-3. And the questions to keep in mind as we go along are 1, how is the malicious code initially called? 2, what does the malicious code do? 3, what URL does the malware use? And 4, what file name does the malware use? When you first open up the lab15-3.exe file in IDA Pro, it's not readily apparent what's going on. There are some potentially malicious function calls that are imported, but they don't appear to be used in a section of the program that's actually executed. It turns out the program is intentionally crafted to overwrite the return address of the main function to redirect the flow of the program into the otherwise uncalled region that contains the malicious function calls. Starting at hex 40100C, the address to the malicious code block is assembled, and on the move instruction following that, EBP +4 is overwritten with it. If you press Ctrl K in IDA, the stack frame window appears, and on here you can see that the return address is overwritten with the crafted address. In this way, when the return function is called at the end of the apparently legitimate main function, the malicious section of instructions is called. This is the answer to question 1. The malicious code is initially called by overriding the return address in the main function stack frame with the address to the malicious code. We can now continue our analysis by following the crafted return address to hex 40148C. Doing so leads us to the next anti-disassembly technique at hex 401492, which is a false conditional branch in the form of an XOR EAX instruction followed by a jump 0 instruction. We can apply the same fix of cutting out the rogue byte that we've been using over and over again throughout this demonstration, and move right along. The previous fix reveals the construction of a structured exception handler that's located at hex 4014C0. This is closely followed by a divide by 0 instruction that triggers the exception handler. The extra instructions after the divide by 0 are never executed since execution is handed off to the exception handler. IDA interpreted the bytes at the exception handler's address as data, so we start by converting them to instructions so we can analyze what they do. The first instructions unlink the structured exception handler and remove the exception from the stack, which basically means that it's cleaning up the error. A normal series of structured exception handlers would kind of hand control back to the regular program at this point, but this one was crafted to do malicious things after that. Let's find out what they are. Continuing our analysis, we find an impossible disassembly of an instruction jumping into itself at hex 4014D7. We can fix this by converting the jump into data, then cutting out the rogue byte. Following the flow of instructions further down, we find a call to the URL download to file A function. The second and third arguments of this function are the URL to download from and the file to download to. Since the global memory locations at hex 403040 and hex 403010 are pushed onto the stack in location of the second and third arguments, they must contain these values. Looking further up, these memory locations also both appear to be acted on by the function located at hex 401534. We'll take a look at the memory locations themselves first. At first glance, both locations appear to contain nonsense. Hex values don't decode straight into readable ASCII strings here. So next we'll take a look at the function that interacted with both of these locations. The function that interacted with the memory locations was at 401534, so that's where the image is taken from. In this function, we find an XOR operation that is used to decode the data held in the global memory locations that we looked at before. Each byte at those locations gets XORed with hex FF, and after decoding the data using this function, the plaintext arguments for URL download to file A are found at those memory locations. After decoding, the URL practicalmalwareanalysis.com/tt.html is located at global address 403010, and the string spoolsrv.exe is located at the address 403040. Continuing the flow of instructions after the URL download to file A function, we find one more anti-disassembly technique. It's another false conditional branch that we can fix as usual. Cut out the rogue byte. Finally, the last portion of this malicious section executes the spoolsrv.exe file that was downloaded before. So here are the final answers for Lab 15-3. The purpose of the malicious code is to download and then execute a file. The URL is practicalmalwareanalysis.com/tt.html, and the malware uses the file name spoolsrv.exe. And that's the end of my coverage for Chapter 15 Labs from Practical Malware Analysis. To summarize everything, disassemblers have to make assumptions when analyzing executable files, and these assumptions can be exploited by malware authors to make confusing disassemblies that are difficult to analyze. And there's all the techniques that I covered. I won't read them out again. And I just want to say, this is just the tip of the iceberg. Like all things computer security related, it's a constant cat and mouse game. The book this presentation is based on came out in 2012, so there are many other techniques documented now. As disassemblers get more sophisticated ways of undermining them may be discovered. And I found a resource called Unprotect Project that details a bunch of anti-reverse engineering techniques. And their page about anti-disassembly referenced a number of techniques not covered in the book, including opaque prediction, code transposition, register reassignment, API obfuscation, and more. And these are beyond the scope of this presentation, but I thought they were worth mentioning just to give a glimpse at what else is out there. As stated previously, nearly all the content of this presentation is based on the Practical Malware Analysis book, but here are a few extra sources, including some about function pointers, one about structured exception handlers, and a link to the Unprotect project site that I referenced on the last slide. And with that, I'd like to thank you for your attention. I learned a lot during this project, and I hope I effectively communicated some of it to you. And if you have any questions or comments, feel free to email me at the email on screen or comment below. Thanks.